And bam. Okay. So, oh, stupid. Oh, it's not stupid. Aha, at some point you do have to plug the computer in. Okay, so question 1, draw a truth table for an AND gate, then create a circuit that implements an AND gate using only NAND gates. So, does anybody want to guide me in constructing the truth table for AND? Volunteer. Innocent.
So a truth table, you just say A and B.
So A, B.
And
Okay. Now help me fill it in.
0, 0, 1, 1. 0, 1, 0, 1. In the first one, 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. And 1 and 1 is 0.
Okay. Next part. Could be or could be someone else. V.
So we take an AND gate.
Okay.
Has two inputs.
Mm-hmm.
Wait, so do I have to like?
We're spelling out the circuit.
Can I go up and draw it?
Oh, absolutely. That sounds great. Here, I'll erase what I started. And then what I'm going to do is I'll park this truth table over here. And then, yes, come right on up.
Thank you so much.
And literally right on up.
Okay. Oh, no, that's
Oh, whoops. Yeah, I was on eraser. Sorry, it sabotaged you there.
sabotage.
What do y'all think? How'd you do? Excellent job. Excellent job. Any questions on problem 1? So the general theme of this practice problem is that you should be prepared to do this basically for any of the basic 1-bit circuits, right? So for AND, OR, and NOT, you should be absolutely ready to do them from NAND gates, straight. For like multiplexers and demultiplexers, absolutely ready to do them with AND, OR, and NOT. Okay. And really anything else. I might give you just some bizarre truth table and then just say, build me a circuit. So we'll see where that goes. All right, problem 2. Why is the 2's complement important, and illustrate its importance with an example? So somebody tell me why 2's complement is important. Why is it important? Yeah, Innocent.
So it helps us to represent negative numbers in binary. So I want to take example. Let's take something like 3 in binary, 0, 1, 1. And then its 2's complement is 1, 0, 1. And if you add them, you get 0. Because 1 negative.
So this is pretty good, right? I mean, this is actually a 0. Sorry about that. So it says, okay, this is a way to represent negative numbers in binary. And the reason it matters is if you find the two's complement of a value and then add it to the original value, you get 0. This then gives us a way to represent subtraction by reusing addition circuits. So that's something I would really be looking for in this part of the answer, is we get to subtract, for free, so to speak. It's not really for free, right? You have to be able to do the two's complement, but you effectively get subtraction for free by using two's complement arithmetic. And, I hope you came to an appreciation of this when you built the ALU in chapter 2. So, of course, this question, I could ask it directly. In fact, I have in the past. But it's also getting at being ready to talk about how is two's complement actively used in our machine. So it wouldn't be out of bounds for me, for example, to put the truth table for the ALU, or not really the truth table, but a little, these bits do these things and do these calculations. I could imagine putting that straight on the test and then asking you to explain, well, how does this combination of control bits get me A minus B? Or just negative B or whatever, or negative Y. It was X's and Y's. The point being, I want you to have an understanding of this at a sufficient depth that you can explain fundamentally how it works and why it's a valuable circuit saving device. We don't have to reinvent subtraction. It's just addition, but with these funky values. You should, of course, also be ready. This question didn't really ask it, but you should also be ready to perform a two's complement. Of course, it implicitly asked it because it demanded an example. But I might ask a question like, define how two's complement operates. And then you'll need to be able to say, well, you do the thing with the bits and add the 1 and so forth. So coming into the exam then, I'm really expecting you all to have a really good grasp of two's complement. And in one form or another, I'll certainly be assessing it. Any questions on this? All right, examine the truth table below, then answer the following questions. What operation is performed by a circuit that implements this truth table? Yeah, Savvy.
I said it was a half adder, the first being the A input, the second column being the input, the first output in this sum, second output being the carry.
That is correct. This is a half adder. So something that you see from both questions 1 and 3 is I'm expecting you to know these sort of basic building block operations well enough that I can throw a truth table out there and you should be able to tell me what operation that is. So and or not, mux, demux, half adder, full adder, all this stuff. I pretty much expect you to know it. And this problem is an example of that. All right, so now we're going to create a circuit corresponding to this truth table. You may use and, or, and not gates. I like what V did earlier. Do we have a volunteer to come up and sketch the circuit? Volunteer. And, or, and not. Half adder. Jack, great. All right, here you go. Try it out.
I just feel like I'm gonna. Oh yeah.
The beauty of this is you can undo anything you write. You can erase, and don't forget, no matter how bad your handwriting is, mine's worse.
I don't know. I'm a pretty good contender.
Okay, well, we'll have to put it to a vote.
Wow. Oh. Let's begin with into. Out to.
Okay.
And we have into going to. Or into coming in here. And going to the other side of the order. I'm going to and this is out one. What needs to be the output of this? This is and with into thing. Oh, I changed my color. It'll be
It suddenly became green.
Mhm. We're gonna knot it and then put it on the out. Yes. So out two is just anded together first, and that gives us our out one. And then we
Oh, so the out 2 is the carry.
yes.
So your point is if it's a half adder and they're both ones, you're going to carry. But in any other situation, you're not going to carry. So it's an and. Good. Okay.
And then we want to what do we want to do? Yes, we want to exclusive or the other two inputs. And
That's
to
right.
do that, we need to and an or and NAND. So we first make our NAND here by making an and, then a not, and then make an or between the two, and then we AND them together, and that should give us an exclusive or 0, 1, 1, 2.
Yeah. Good. So what do you all think? Does that look like the half adder? Yeah, so Jack did a nice job here. Really nice job. Let's glance back for a moment at the truth table. So for out 2, part of the fun of this, right, is when you see it in truth table form and you get so accustomed to these things, you think, oh, wait a minute. Out 2 is 1, 0, 0, 0. Where have I seen that before? And sure enough, it's an AND gate. And you can kind of read it out of the truth table, but you can also think about it logically, right? If I'm adding 1 and 1, that's the only time I get a carry. Any other add, I'm not getting a carry. You can think about it both ways. Then he correctly observed that out 1 is an exclusive OR. That is an OR which works unless they're both true. And then it doesn't work. That's what makes it exclusive. It excludes them both being true. And so, yeah, he did a fairly clever job with this. So for the exclusive OR concept, he thought, well, I'm just going to OR them. And then using this AND gate in combination with the AND and the not, and it would be fine with me on a problem like this if I say you can use AND or not. You can use NAND, directly. That would be fine. So you effectively NAND the 2, and when you NAND them, if they're both 1s, you get a 0. Otherwise, they're all, oh yeah, good. Otherwise, they're all 1s, right? And so that masks out that exclusive condition, and bam, there it is. Good job. All right. Problem 4, examine the truth table below, then answer the following questions. It's as if you, oh, sorry, Spencer. You have a
Would
question?
you be expecting us to draw out like as a circuit?
You don't have to. If you write it out in the HDL, that's absolutely fine with me. Yeah, because that's what you've been doing. All I really care about is, do you understand how to combine the inputs to get the output? You can express it as a drawing, and that's great. You can express it directly in HDL, and that's also great. Great question. All right, so yeah, that 3 and 4 were both this kind of thing might suggest that you should expect a lot of these. Okay. Examine the truth table below, then answer the following questions. What operation is performed by a circuit that implements this truth table? Anybody? Anybody recognize this circuit?
It's a demultiplier.
It is a demultiplexer. That's correct. So let's review how it's a demultiplexer. So input 1 and input 2 represent the values, well, wait, no, one of them is a value and one is a select bit. Yeah. So input 1 is a value. Input 2 is a select bit. So because input 1 is a value, if it's 0, all the outputs just go to 0 because there's no signal to be routed at that point. So if input is a 1, which output gets activated depends on the select bit. So if the select bit is a 0, out 1 is 1. If the select bit is a 1, out 2 is 1. And that gives us a demultiplexer. Now we need to create a circuit corresponding to this truth table. This has been fun. Any volunteers? Any volunteers? Andrew, come on up. Right, that path is doable but slightly hazardous. For some mysterious reason, there's a podium here. Here you go.
Thank you. That's for number 2.
Mhm.
Supposed to be.
All right. What do y'all think? How's that for a demultiplexer? This is a really nice solution. Let's talk about why it makes sense. So when we think about out 2, again, kind of like on the last one, we can see, oh, there's a pattern. And the pattern looks really familiar. It looks so familiar that I can just deploy an AND gate, and I've got it. Now, the next pattern looks less familiar. However, if I've got 1 bit out of 1 and 3 bits out of 0, I know I can somehow do this with an AND gate as long as I not something. And that's precisely what he did. So you've got this, you want something that looks like that. So you knot this thing and it works. So that's one way you can approach the design. Another way you can approach the design is just to think about the larger concept, right? So if my input is a 1 and my select is a 1, and I know I want it to go to out 2 and the select is a 1, I can just AND them, knowing that in other case would I want a 1 there. If my select is a 0, I want it on out 1. Well, if I just knot this, I can use an AND gate and bam, I've got it. So different perspectives or starting points, same basic destination. Cool. Any questions on problem 4? Problem 5, explain the process by which a CPU executes a machine language instruction. Any volunteer ready to explain how a CPU executes a machine language instruction?
Question about it.
Yeah.
For this, you want to focus more on which each bit in the instruction has the program do, or what the program does, where it stores the like instructions and addresses and stuff inside the program.
So that's a great question. If I write a question that's as generic as this, then you don't necessarily have to express it in terms of the book CPU. So for a question like this, a CPU, what I'm really looking for is what would any CPU have to be doing for it to be a CPU? In your answer, you might use the machine from the book as an example, and that would be absolutely fine. It's also possible for you to ask a more direct question like, in the hack architecture, how does it decide when to jump? And then you would absolutely need to be referring it to those terms. For this specific question, though, I'm just really looking for, what is it that any CPU does? Yes, Innocent.
I mean, I explained it in like an individual way by saying something like, it gets an instruction, and then it gets data from memory. Then use ALUs to perform operations on that data. Update memory state, use group and counter to go to the next instruction, and start converting.
So that would be mostly right, except that it didn't address the idea of a jump. Right? So what I would be looking for then, so the key ingredients then are as follows. First, it has to fetch an instruction via the PC and whatever your instruction memory it happens to be. So the program counter tells you which instruction to fetch from the program memory. Next, it does kind of two things in parallel. First, like Innocent mentioned, the ALU calculates something. And then kind of in parallel with this, we have change in registers or RAM. Then, we determine a jump, and if so, we have to change the program counter specifically. And then we loop back up. That is, come back up, fetch the next instruction, and so forth. So I wouldn't absolutely require it, but it wouldn't hurt to say something about the role of the clock here. So all of the memory updates, including the program counter, all happen at the same time, and that's what enables us to go and fetch the next instruction. So those are kind of the essential ideas of what a CPU does to decode an instruction. You might also include something to say something about the instruction bits, decide, possibilities. And so that would be references to the ALU, what changes does it make in RAM, what happens with the jump. And so I would look for something like this as well, to say something about what's the role of the instruction bits in a CPU. But in a nutshell, that's basically how a CPU decodes an instruction. But like I mentioned, it wouldn't be out of bounds for me to ask a specific question about a specific kind of decoding on the hack machine. I might make up a machine and ask you to tell me how it's going to decode something. I mean, there are lots of possibilities here. The essential concept I'm going to be assessing is how well do you really grasp and internalize what it means for a CPU to decode an instruction. I might ask it 20 different ways. That's the essence of what I'm going for with a problem like that. Any questions about this? There will definitely be a few questions of this flavor on the exam where I just ask you, in your own words, how does X work? And then what I'm looking for in questions like that is I'm trying to determine, have you grasped what I think are the key ideas about that, and can you express them in a way that convinces me of that? I don't necessarily want you to give me a word avalanche. Sometimes a bulleted list is fine, or what have you. to really just focus on what are the really core essential ideas behind this. You could even think in terms of, if a computer science 150 student asked me about this, how would I explain it to them? As a way of a technique of trying to break down what are the essential core ideas that are encapsulated in what is being requested. Other questions about this? All right, so question 6. This one is a lot of fun. So let me say from the outset, there will absolutely be a question like this, where I give you some kind of Python-like pseudocode, and you're going to write out the assembly code. And so this is really assessing how well have you grasped the assembly process. Specifically, do you understand the assembly language well enough that you can just look at some higher level program and write down what it looks like as a lower level program? So, any volunteers to translate this masterpiece? Yeah, Innocent.
I think my assumption is correct.
Well, we're going to give it a look. All right. The pen is yours. Okay, there you go.
Okay. So
All right, yeah, you can go ahead and explain it if you'd like.
my
Oh,
ration,
oops, too far.
my rationale for this problem goes like the following. It looks like you have an infinite loop. That means it's going to be jumping over and over and over again. So I was like, if m at this location is equal to 0, they were encoded that. I was like something like, at this address, give me the value in that memory, and then I can jump to assign if that value is equal to 0. So let me assume it was equal to 0. I jump to assign. When I jump to assign, I take this value, and then I save it to my D register, and then I look back at memory, this number, and then I keep the value that I had in D to that memory, and then I look back at the beginning. So if in that position that value was not equal to 0, what's going to happen? It's going to go back in this loop. Well, actually, m it's equal to 0, not D. Yeah.
Oh, okay.
Yeah. At this location, put that 0 and then jump at the beginning. I don't know if that's, yeah, that's kind of fun about it.
What do you all think? How do you do? So he nailed it. Absolutely nailed it. Perfect job, Innocent. Well done. So, what are some essential ideas we're looking at here? Here, actually, well, okay, I shrank it way too much. Okay, I think that's all right. So, this is Innocent's complete solution. Let's look back at the original program. So while true, Innocent correctly identified that as an infinite loop. If m of 24,576 equals 0, m of 16,384 equals 255. Otherwise, m of 16,384 equals 0. Simple, innocuous program, extraordinary amount of assembly language. So one thing you should infer from this is whenever I ask you to translate a program, it's going to be pretty simple, okay? I'm not going to ask you to do anything crazy complicated. You know, we might go a little bit beyond this. I might want you to add something or whatever, you know, that kind of stuff could happen. But I'm not going to be putting a half-page Python program on there for you to assemble. That would be kind of absurd. Just given that you've only got 75 minutes to complete this. So one of the insights I'm hoping you're starting to get, having done project 4 and now looking at project 6, is that a lot of simple language constructs, like an assignment, have what you might call a stereotyped assembly language equivalent. So if I want to say some value equals some other value, it's really going to look a lot like this, right? I mean, I'm going to say x equals 5. I'm going to have at the value d equals a, at where it's going, m equals d. And so this is a stereotyped pattern that will recur in any program that has an assignment. Similarly, if I have an if, I know that I'm going to have to get the value I'm comparing against into my D register. I might have to do some arithmetic on it. So if I'm just wondering, are these two values equal? Well, I'm going to need to subtract them. Subtraction is how comparison happens. Rephrased right, anytime you've got a comparison like x less than y, that's always the same thing as this comparison. And because our ALU flags are only relative to 0, so you can say it's 0, positive, or negative, this kind of a subtraction is how a comparison traditionally would occur. The point is, when you're ready to do your comparison, you somehow got to get into D, and then you're going to have to do a jump. And the way it's structured here looks weird, but makes a lot of sense. It looks weird because we jump if it's true, which means the else code came first, and then the if block came second. There's nothing semantically meaningful about that. It's just that the layout of the program in the high-level language isn't necessarily going to be the same layout when you get down to assembly language. And you need to be prepared for that. If you try to force the structure to look the same, then you have to start doing weird stuff like, once you get everything in and you do, you got your value in, you have to knot it or something before you do the comparison. It just gets very messy. I find it a lot easier to code like this. So those are some core essential ideas. Be ready to think about, for every basic high-level operation, what does it look like in assembly language? What does a loop look like? We see it right here. What does an if look like? We see it right here. What does an assignment look like? Again, we see it right here. Trust me that I'll make sure that it doesn't require an excessive amount of assembly code. I'm going to be aiming for it to be something roughly like this. Could be a little longer. It shouldn't be hugely longer. But absolutely guaranteed you will have a problem like this. And it will not be this problem. Yeah, Innocent.
So is it one of those last ones about like screens and keyboard?
If I do, I'm going to tell you what those memory locations are. Right. So this problem is sort of amusing in the sense that knowing where keyboard memory is and where screen memory is, you can look at it and actually figure out what it does. I heard Jack mentioning, oh, it's putting this 8-pixel dash up in the upper left corner. Just giving you those memory locations, I'm not going to expect you to tell me that. But I might do a problem where I say something like, write an assembly language program that puts a dash in the middle of the screen. The screen memory goes from 16,384 to 24,575. Or make a dash appear in the upper left corner if a key gets hit or not or something. I could do that. But at that point, I would tell you, these are the locations of the memory mapped I/O. I wouldn't be requiring that you have those memorized. That's not really getting at the core ideas I want to assess. The core ideas I want to assess are, what does a high-level program begin to look like as a low-level program? Or how do you write an assembly language program? Giving you the high-level program is kind of an easy way to do that. And maybe what's at the heart of doing I/O in assembly language? Do you understand the memory mapped I/O concept? And again, there are 20 different ways I could assess that. I could ask you to write a program to do something. I could ask you to explain it. I might give you an example assembly language program, say, this is screen memory, this is keyboard memory. How does this work? What does it do? I might do that. But it all comes back to, if you understand the essential concepts, no matter how I ask you about it, you should be able to answer it. Any other questions? Is everybody at least slightly less terrified of the idea of a midterm on Tuesday? At least slightly less terrified. All right, so any questions on creating an assembler? So, we went over this in a lot of detail last time. I don't have any prepared material this time in that regard, but I'm happy to answer conceptual questions you might have, go back over the example from last time, whatever you want.
I was meaning to talk to you about this in office hours.
Okay.
And we've done it in our homework in the building CPU. But this process of determining a jump from JBit, I don't think they quite understand it very, very well.
Okay, let's go over it again. It's a great question. It's a great question. I'm glad you asked. So what Innocent is asking is, how do you determine when a jump happens? So I'll go over it both in terms of the assembly language and in terms of the machine language. So in terms of the assembly language, we have the semicolon, we have something from the ALU, and then we've got a jump instruction. So that's the basic structure of a jump instruction in the assembly language. So let's go over in a detailed way what the real possibilities are here. The ALU outputs that are, so to speak, live options are ALU outputs that don't make use of the A register or of memory. And the reason for that is we have to load the A register with the jump target before we get to the jump instruction. So unless there's some incredible coincidence that the jump target also happens to be a location in RAM that has pertinent data, you really aren't going to want to have something like D minus A over there. Or D minus M. I really don't recommend it. As in, I can hardly even imagine why someone would do that. So the live options then are constants, right? So you could certainly imagine having a 0, a 1, whatever, and then the D register. Because A and M are just really not contenders. Not out of the question, right? It would be something like D plus 1, D minus 1, negative D, not D. You could do stuff like that. But you're not going to have A or M involved in the ALU condition. If you're feeling really clever, maybe you'll even do something like, give it a destination. D equals D plus 1, and, jump if it's positive or something. There might be some really clever loopy thing that you might do that way. Not terribly likely. All of that said, I know at least one of you is going to come up with one just because I said it. We'll see. Okay, so that's the ALU side. Now we get to the jump side. So there are a number of distinct possibilities that we need to consider on the jump side. So first, we can think about the three possibilities where exactly one jump bit has been set. So is JGT, JEQ, and JLT. So how do these relate back to everything else we're doing? JEQ happens when whatever you did in the ALU results in the ZR flag being a 1. By whatever you did in the ALU, I mean this part of the expression right here, the part before the semicolon. Okay. JLT, jump when you're less than 0, happens when the NG flag has been set on the output of the ALU. And then JGT can happen when neither the ZR nor the NG flags are set. And you might remember that from building your CPU. Okay? So that's fine as far as it goes. So the process at the CPU level is a matter of addressing, well, there are these 3 bits. You know, one's greater than, one's equal to, one's less than. So you take that bit and you AND it with the ALU condition that corresponds to it. And when you AND it, if the result of the AND is a 1, then you're going to have that 1 be the load bit on the program counter. And that's what makes a jump happen. Now we've got some others of these, right? So we have, for instance, JNE. Well, JNE is essentially just a JGT or a JLT. In other words, at the CPU level, you might remember having to combine all of these conditions with some OR gates. Because if any of the 3 conditions mark a jump, you're gonna jump. And so we can think about the meanings of the other jump instructions in terms of which pairs of these they include. So something like JGE is the OR of JGT and JEQ. In other words, it's literally greater than or equal to. Then JLE is the combination of JEQ and JLT. You're jumping if less than or equal to. And then finally, we've got the great unifying jump of all. If you put all 3 of these as a 1 in the instruction, you get JMP. That is, if you're going to jump if you're less than 0, if you're going to jump if you're greater than 0, and if you're going to jump if you're equal to 0, let's face it, you're going to jump. And it literally doesn't matter what the ALU says. We have exhausted all possibilities. You must jump. Gun to your head, you are jumping. Kind of kidding about that, right? Now, what if they're all zeros? If they're all zeros, this doesn't appear in the assembly language instruction at all. Yeah. So if you've got an assembly language instruction with no semicolon and no JXX, all 3 J bits are 0. From there now, if you've got your semicolon, and you've got then one of these 7, which you will, because like we discussed last time, error handling is outside the scope of the assignment. You can assume legal inputs, okay? Then it's just a matter of determining for each of these 7, what do those 3 bits look like? What would I do in my solution? You can probably guess. I've got a dictionary. 7 entries, the correct 3-bit pattern for each entry. Yeah. There's nothing about the text of JMP that readily enables one to extract 111 other than just knowing that JMP lines up with 111. You know, some of the others you can kind of do that, right? Like if it's got a G in it, that G bit is set. If it's got an L bit in it, that L bit is set. But then things get really nasty. You can't just sort of say, well, if that letter E is in it, then you're going to use the 8E bit. Well, not really, because JNE is like the total opposite. So in this case, I found it easier just to make a dictionary with 7 entries and then just ask the dictionary which of these has the right bit pattern. And then I just paste it on there. That's pretty much how I did it. No semicolon at all, 3 zeros. So, that answer your question, Innocent? I mean, yeah, the jumps are really intricate, even on this CPU, to say nothing of a more sophisticated CPU. But the essential idea is just the instruction bits indicate a condition. You examine the output of the ALU relative to that condition just by ANDing. You OR together all possible conditions, and that ultimately feeds to the load bit of the program counter. And bam, you got it. Cool. Any other questions I can help with understanding the assembler? That was a good one, Innocent. Any general questions? Well, you know what? I'm just going to call it a day early today. So go work on your assembler. Think about the exam. I'll see you Tuesday morning. Anybody want a private chat? Just stick around. I'm not going anywhere. 15 minutes. You want me to look at a solution, go over whatever you need? We can chat right now. So that's it for today. I'll see you Tuesday, if not before.